Okay, thank you very much, David, and thank you to the organizers for putting on this wonderful conference and allowing me to come and enjoy this, this mission of getting computer scientists, statisticians, mathematicians, practitioners all together. And so I've benefited enormously from that opportunity, and I'm not sure that I'll be able to return the favor, but I'll do my best over the next half hour or so. I'm going to describe some work that my colleague at Rice, Dan Sorensen, and I got involved with last fall semester when I was still at Rice, and we were teaching a graduate seminar on random matrix algorithms, and really enjoyed learning a lot about that field and even more today. And I moved to Virginia Tech this past semester, where I'm helping to start an undergraduate program in computational modeling and data analytics that also espouses that same interdisciplinary approach that this conference has. So it's really great to meet a number of new and interesting people here. And if you have thoughts on what undergraduates should learn about machine learning and computational modeling, would love to chat. Okay, so we already had a CUR factorization talk on Tuesday. It was an optimal CUR factorization talk, so I can't necessarily even promise optimality, so you might want to sink into your chairs a little bit and close your eyes. But let me just recap, because that was 48 hours ago, and maybe it's a little stale if you're not used to these factorizations. So the idea is that we have a matrix A, which may be, of course, large or massive, but maybe it's either low rank or it can be well approximated by a low rank matrix. And so the game is to write A as some subset of its columns times a special matrix U times a subset of its rows. And that the whole effort here will be to figure out which of the columns of A to extract and which of the rows to extract, and then we'll find U in such a way that we do the right thing with the approximation. So of course you know how to do this, and in theory at least, if we don't constrain C and R to be columns and rows of the matrix. Of course we have the optimal approximation through the singular value decomposition. So compute a singular value decomposition or some kind of approximate singular value decomposition, and we have the truncate after k steps, we have an optimal rank k approximation. And so that's the best we can do if we're interested in just minimizing the 2 norm of the error, the Frobenius norm of the error. But those singular vectors are lacking in some ways. So first of all, if A is a very sparse matrix, as we've heard before, the singular vectors generally won't be sparse. And so we have now lost that property of our vectors. Maybe the matrix itself has 0, 1 entries, or non-negative entries, or integer entries. All of those properties will be lost by the singular vectors. And moreover, those singular vectors will be maybe hard to understand in terms of our application. So maybe we can look at the first singular vector and we can interpret its meaning, but then the next one's orthogonal to it. And so trying to extract some kind of deeper meaning from that can be a challenge. Whereas if we actually have columns and rows, we have real data that we can look at. We can look at representative members of our data set. And that's the game. Okay, so I love this motivational example that I think I saw in a paper of Mahoney and Drenaeus from 2009. So imagine we have just a tall, skinny matrix with only 2 columns. And the idea is that each row of this matrix are coordinates in the plane for a point from one of 2 multivariate normal distributions. And those 2 multivariate distributions have different principal axes, and so they form a kind of X in the plane. And it's not an orthogonal X, it's a skew X. So if we just compute the leading singular vectors for this matrix, we're going to get orthogonal vectors. And because the variance of this distribution is about the same, the leading singular vector, the longer of those red lines, is really somewhere between the 2 data sets, and then the second one has to be orthogonal to it. Whereas if we use the kind of CUR factorization I'm talking about today, we get one column, one row of our matrix and another row of our matrix that are real pieces of data that I've extrapolated a little bit there, and they're very representative of what the data set is all about. And that's the kind of thing that we hope for in much more complicated applications, obviously. So there are many ways to compute CUR factorizations, and they really sort of emerged in the 1990s and some of the numerical linear algebra literature that I'm more familiar with. For example, Pete Stewart looking at column-pivoted QR factorizations and pointing out how you get a CUR factorization from this. And then these ideas in volume optimization, where you're trying to maximize a certain determinant that Evgeny Tretichnikov and others have pioneered. Uniform sampling of the columns. So that another problem, and a little bit more akin to what we were looking at in terms of optimal complexity on Tuesday, maybe we're not going to want to even touch all of the data. how well can we do if we're going to try to get really tight optimal complexity. And then this idea of leverage scores. So here we're going to allow ourselves to compute a singular value decomposition at the start, or maybe just an approximation to it somehow. And then we're going to take norms of the rows of that singular vector matrix. And we'll call that a leverage score, and there are various refinements and enhancements to that idea. And that will give us some idea of which of the rows are most prominent in the singular vectors. And so that's this idea behind the Mahoney-Drenais CUR factorization I just referred to, and many, many other ideas. I give only a sampling of ideas based on leverage scores. Now, our idea in this talk will be spiritually similar, in that we're also going to need the singular vectors, or an approximation. And so later in the talk, I'll show you some numerical examples, and I'll be comparing those to leverage scores, or at least a kind of deterministic version of leverage scores, to compare apples to apples. Okay, so how do we pick columns? How do we pick rows? How do we form U? We're going to get to all these questions. But I want to motivate it a little bit, particularly for kind of a broader data science audience, by describing a particular compression problem that's very common in model order reduction for large-scale dynamical systems. And it's that problem that really gave rise to something we call discrete empirical interpolation, and that will be the method that we then use for choosing our columns and rows. And so we'll have a little bit of model reduction here at the beginning. And then I'll explain this way we pick indices, and how that gives us a CUR factorization. I'm actually going to do some error analysis and then show you a few examples. And this is not, I'm not claiming that this is a perfect method or a complete method or always better than everything else. It's another tool in the toolkit. Okay, so the model reduction problem. We're thinking of a differential equation. The derivative of a vector is some potentially nonlinear function of that vector, and time, for example. And we're thinking of this dynamical system evolving in, for a three-dimensional model, maybe in a billion-dimensional space, a very, very large model. And what we'd like to do is somehow figure out a lower dimensional manifold on which the dynamics evolve. And if we can then capture the dynamics on a low-dimensional manifold, we can do all kinds of things with simulation and design on that lower dimensional space. And so the way that we'll get that low-dimensional manifold is to take snapshots of our dynamical system. We'll evolve it in time, for example, using a numerical integrator, and then we'll just take time samples of that system. We'll call those A1, A2, etc. We'll stack them side by side in a matrix. And of course, you're already saying, how do you pick the times, the samples? How do you know you've gone deep enough into the dynamics to capture all the system? Those are big problems. I'm not going to talk about that. I'm just describing a matrix. This is where we get our data from. And then we'll identify the dominant manifold. We all know how to do that, right? You just are going to compute the singular vectors. So I want to give you a particular example, a linear problem with a heat equation, to give you some idea of why the singular vectors of this snapshot matrix might decay very quickly. So a heat in a bar in one dimension, so this wiggly curve here is a heat distribution at time 0, and then I'm going to step forward and I'm going to take a few other snapshots, and I'm not showing you all of them, but what you should notice is I'm advancing in time. Doesn't that solution look kind of like a multiple of the earlier solution? So it looks almost like we're just scaling. I'm going backwards in time, forwards in time. So if we make that function the columns of our matrix, it's no surprise that the singular values decay very rapidly. Now, of course, I could give you other dynamical systems where they behaved worse or perhaps even better, but you get the gist. These snapshots all look very similar. The dynamics on a low-dimensional manifold, we can capture the dominant subspace with the SVD. And so that's great. And for linear problems, that would be fine. But there's this weird thing that happens for nonlinear problems, that you can do a dimension reduction by taking your dynamical system and writing it as a linear solution, approximating it as a linear combination of your basis functions, and imposing a Galerkin condition to turn that into a square system, and then getting a nice, small, low-order dynamical system down here, where y lives in 30-dimensional space instead of a billion-dimensional space. A very, very effective method. But there's a problem, and it's that function f of vky. So you have a short vector y that you're then multiplying vk against. So you're expressing your approximate solution as a linear combination of the singular vectors. That's a very long vector. You're then evaluating the function at that vector. So even though the dimension of the problem is now reduced, the work hasn't been reduced. In fact, if you do this method, even though the dimension's reduced, it can actually take longer to evolve the dynamics than the original system because of the overhead in constructing the approximation. And so it's kind of an elegant idea to compress to this subspace, but it fails to be practically effective. And so the way that we actually make this work is to come up with some way of approximating this nonlinear function by compressing f and only evaluating f onto some lower dimensional space and then interpolating. And the idea that I'll be describing to you, discrete empirical interpolation, really began in the finite element community from Padura and others. And then Dan Sorensen and his student Saifon Chaturantabut, who just won the honorable mention for the Householder Prize last week, then developed this and generalized it. And I'll be really describing that approach. Okay, so DEIM is the way the Germans like to pronounce this, so we'll follow that. How does this procedure work? Okay, so I need one tool, and that's this notion of an interpolatory projector. I love projectors, projection matrices. And this is a very, very special kind of projector. So the idea is that we're going to have some matrix V and some selection of indices. So we're going to pick from among M indices. We're going to choose K of them. And so often, if we have this matrix V that has orthonormal columns, we could form V times V transpose, a beautiful projector, the orthogonal projector onto the range of V. And if those columns of V are your dominant singular vectors, then this is a projector onto the dominant singular subspace. But now I want a kind of nasty cousin of this orthogonal projector. I'm going to construct a matrix P that's just a subset of the columns of the identity indexed by these numbers P1 through Pk. So for example, if P1 is 6, P2 is 3, and P3 is 1, that would be P transpose applied to a vector. We'll extract the sixth, third, and first component. So that's what P does. And now when I form this projector calligraphic P, you see it has V just like pi does. And so its range, the range of P, is the same as the range of pi. So they project onto the same space. But this special P with this 0, 1 matrix is an interpolatory projector. And that means the following, that when I apply P to a vector, just look at the figure at the bottom of the screen. When I apply P to a vector, say that picks out the sixth, third, and first entry, I get a result that matches in those three entries. It interpolates the vector, and it's going to mess up the other entries, but at least it matches in some entries, and it's also in the range of V. So I'm getting a vector in the range of V that interpolates my original vector. A neat projector. Okay, so the orthogonal projector has all kinds of beautiful properties. P will be an oblique projector. But like an orthogonal projector, square it and you get back to where you started. They have the same spaces. We're going to use this kind of projector to build up our indices. Okay, so I'll need some notation. V sub j is just a set of the first j singular vectors. And P sub j is this index matrix that will pluck out the right shifts for up through j of these indices. Okay, so we want to find k indices, where k is some specified number. And now the procedure is actually very, very simple. It's a lot like Gram-Schmidt orthogonalization. And I'm going to try to describe it as easily as I can using these projectors. So I'm going to start with my first singular vector. I'm just going to scan down it, and I'm going to look for the largest entry in absolute value. That star here, that's my first index. Okay? Now to get the second index, if you understand the second index, you have all the rest. This is the only thing that's unusual. I'm going to take my projector onto the range of V1 that interpolates at P1, and I'm going to remove the component of V2 in that direction. So I have a residual R2. It's just V2 with the projected value of V2 out. Now since P2, V2 interpolates V2 at a certain entry, R2 is going to be 0 at that entry, the sixth entry corresponding to P1. Now I just scan through what's left and find the largest absolute value of an entry there. That gives me P2. So now P3, I just have a bigger projector. Now I build the projector onto the first two indices, compute my residual in the same way. Now that residual is 0 and 2 spots because I've interpolated there. I've picked out the largest entry, and then that's now the one I choose for P3. And of course, I continue this k times. The algorithm is here. I actually kind of put some fluff in there to make it look longer than it really is. There are about 2 germane lines there. There's the computation of R, and then there's just computing a max. And so you ask, how expensive is this? Well, I have to compute the inverse of Vj minus 1 in the P entries. So at each step, after 3 steps, I have a 3 by 3 matrix, Vj minus 1P in all of its columns. Okay. Yeah, oh, yes. Okay. So do not implement this with inv in MATLAB, okay? That's a cardinal sin, yeah. That's a backslash in there, but for clarity, I put an inverse there. But I'd lose my linear algebra membership card if I actually typed in. I have those X's on those letters on my keyboard. Good. So this is all it takes. It's a very fast procedure once you have V. And so how do we take these indices and turn them into now a CUR factorization? Well, we take the left singular vectors and we compute row indices. The right singular vectors compute row indices, column indices. So we just do this procedure twice. Once on my singular value decomposition is A equals V sigma W transpose, because U is the central matrix in the CUR factorization. Okay, so I have this nice procedure. Extract the rows, extract the columns. That's all there is to it. How do you choose U? Well, here are 2 ways to choose U, and this is not particularly new, I don't think. If you just choose the kind of intersection of your rows and columns, and you get a square matrix. I've just taken k rows and k columns. We could do something differently if you like. And you invert that matrix. Maybe you wouldn't inv it. You then actually get a CUR factorization that interpolates A at that intersection, okay, which is nice. And so if we then have an alternative method that's a little cleaner theoretically, where we have U written as the pseudo-inverse of the columns times A times the pseudo-inverse of the rows, which is a small matrix. And that has beautiful theoretical properties because we can actually write some things out as projectors, as we'll see. And so that's the choice that we'll take here. But whether we actually even need to compute U is another question. If we're just looking for representative columns, maybe we're happy just applying this DEIM procedure to get the columns, and we can move on to solve our application. Okay, how about finding these SVDs? Well, if we have a tall, skinny matrix, it's really hard to beat MATLAB's built-in dense SVD, the economy-sized version. That's very fast for a surprising class of problems. I've been really impressed by that. If you have really large data, you might think about a Krylov subspace method. You might think about a random range-finding algorithm that we've heard a lot about. I'm going to describe an incremental QR factorization, which is a one-pass algorithm for approximating a rank K SVD. And so this is, if we're really interested in performance, we might think about something like this. So here's the idea. If we have a partial, so say we have a full QR factorization for A, then we can compute an SVD of the upper triangular factor, the R matrix, and that gives us an SVD for A. Okay? And R is much smaller than A was. R is a K by K matrix, so its SVD is trivial. Here's how that works, step by step. Suppose I have a partial QR factorization, K steps of it. So I have K columns of Q, and then a piece of R. And it's not even upper triangular there because I'm imagining they may have chopped some stuff out, as you'll see through this procedure. The goal now will be to just enlarge this QR factorization by one column. So I'm going to append a column of Q and then a little bit of R as well in red. Just using Gram-Schmidt. And we can use classical Gram-Schmidt with a step of reorthogonalization if we like to fix up the Q vectors. Now, here's the key step. I'm going to look at my R matrix, and I'm going to see if there's a row of R that has very small norm compared to the norm of the rest of R. And if so, that means that the corresponding column of Q contributes very, very little to the factorization. And we're going to swap it with the thing we just computed and then chop off the ends and truncate back to basically the same number of Q vectors as we had before. So one-pass algorithm to approximate QR, from which we can then approximate the SVD. Okay. So Now a little theory, and I was going to go on the board, but I don't want to run too late. But I was going to go on the board to prove the point that the theory is actually very approachable. And it starts with a trick that I learned again in this paper from Mahoney and Drenaeus. We'll write the CUR factorization in terms of the U factor I described using pseudo-inverses. And then we'll insert 0 in the form of the CC plus A terms there in red. And we'll use the triangle inequality to bust that apart into two problems. Then we'll use a norm inequality to pull out the CC plus term. And note that CC plus is also itself an orthogonal projector onto the range of C. And orthogonal projectors have 2 norm equal to 1. So that term goes away. And we're left with the sum of these two projections. Basically the amount of A that's not in the column space of C, and the amount of A that's not in the row space of R. A lovely way to break up the problem. So we need to be able to bound terms like that. And I'm going to focus on the second one. The first one's just the same. Take its transpose. And now, Dan Sorensen gave this talk a couple weeks ago in Croatia, and Ilse Ipsen noted, well, this doesn't just apply to your point selection algorithm. This will apply to any way of selecting points, even if it doesn't use singular vectors. So if you hate my method for point selection and you have your own boutique method you want to use, leverage score something else, that's fine, that's great. You can still use this analysis. Equal opportunity. Okay, so R is a short and fat matrix, so we can write it pseudo-inverse in this form. And I'm making all kinds of assumptions about things being full rank and so forth. Okay. And so our goal is now to analyze A applied to this orthogonal projector. And we have one lemma, which I'm not going to go into the details of, which is that we can slot in this I minus the interpolatory projector in front of that expression without changing it. And that's just an algebra calculation. It's a own way of seeing it there. If you're bored in the talk, you can just write that down and just work it out in the rest of the time that remains. Okay, so I lose nothing. I change nothing by putting in that projector, I minus P. Now I'm going to pull out that second projector, I minus R plus R, with a norm inequality. And again, R plus R is an orthogonal projector. I minus R plus R is an orthogonal projector. Its norm is 1. So now I just have this difference of I and my interpolatory projector applied to A. But one of the great things about projectors is, the way projectors upon the same range interact with one another. So remember, pi, the orthogonal projector, and P have the same range. So I minus P times I minus pi is I minus P. And the beautiful thing is that I minus pi was the orthogonal projector that when we apply it to A, all that's left is the non-rank K leading part of A. So now I plug in that I minus pi projector, and I do another norm inequality. And that breaks this problem up of approximating that key term in the error into two pieces. Norm of I minus P. That tells me how far from being orthogonal my projector P is. And then I minus pi times A, which tells me how accurately did I capture the leading singular subspace with my columns of V. So for example, if we want to analyze the first term, assuming P isn't 0 or the identity, the norm of I minus P is the norm of P. Again, a nice paper from Ilse Ipsen proves that identity among a number of other things. And so we do some norm inequalities, and we come up to this key expression, the norm of P transpose V. So select certain rows of V, K rows of V, and look at the inverse of that value. The second term, assuming we use exact singular vectors, is just the K plus first singular value. And so we have this error term applied to the K plus first singular value. The first singular value we're going to neglect. Similar term for C. And so we put it all together, and we get an error bound that gives us a multiplicative factor applied to sigma K plus 1. So that's exciting. That's great. We get the right singular value in there. And now is that 1 plus epsilon? I don't know. I'm only taking K singular values, so you could look at that problem differently maybe and take more vectors and get a 1 plus epsilon there. I don't know. What can we say about these constants? They can be exponentially large. Okay? In fact, you can interpret this DEIM procedure just like Gaussian elimination with partial pivoting. And just like in Gaussian elimination with partial pivoting, you might remember, you can get exponential growth of your growth factor in the matrix dimension, and it's never seen in practice. Again, it's very rare to see these factors grow. I'll show you some examples in a moment. But it would be better to have a good sense of how they work. Okay, so let me show you some special cases here. The first one's artificial. 2 examples, both of which are large, sparse, low-rank matrices with steadily decaying singular values. I can use the same analysis to analyze leverage scores, where I just take the top leverage scores to pick my indices. I'm not using any randomization here. And the same approach for DEIM. And you can see the constants are larger for the leverage score approach than they are for DEIM by orders of magnitude. That's a 10 to the 6th, roughly, where those lines are. And a 10 to the 0 to 10 to the 2 for DEIM. In terms of how well they approximate the matrix A, the singular values are in black. That's the best we could hope to do. DEIM in blue does pretty darn well, and the leverage score approach in red really kind of misses that sharp drop in the singular values. Okay, another approach where I have a steady decay of singular values without that big drop, and leverage score is not as bad in these constants. And again, the constants are just for upper bounds, so that doesn't mean anything necessarily. DEIM a little bit better. And then here's the approximation. And this is kind of what we often see, is that leverage scores do well, and then DEIM does a little bit better. Okay. A couple more examples. One using term document data. Again, this is an example from Mahoney and Drenaeus. And we normalize the rows of A. A is, or the columns of A, I guess. A is 139 by 15,000. And what I'm showing you here are the leverage scores for the columns as black dots. And then the red lines show you the points that DEIM selected. So what you might hope is that DEIM selects points with high leverage scores, that they coincide. And so often that's the case. We see points like up there on the, kind of on the right, but it's not always the case. I'll zoom in on that first 2,000 entries so you can see that a little bit better. And you can see usually DEIM's picking points with reasonable leverage scores, but not always the highest. Here are my constants for that example. And you can see, again, DEIM's constants a little smaller. Here are the errors in the factorization. And here's what you get if you look at the top 10 DEIM points. This is a term document data with terms about Evansville, Illinois, and Miami, Florida. So you expect those kind of terms to be very prominent. And I'm comparing the DEIM points, showing you their kind of normalized leverage scores. So high leverage score means that they'd be likely to be picked. And a leverage score, CUR factorization, and then the terms that go along with it. So we get the key terms coming first and second there. We also get some flaky terms like spacer that don't tell us anything about the data that come in there. If we now look at leverage scores and the top-ranked leverage scores and how they compare with DEIM, DEIM captures a lot of them among the first 30 DEIM points, but not all of them. The ones it misses, like clear pixel, I'm not too worried about. Now, if we didn't use all the singular vectors to compute leverage scores, but only use the leading 2, then the terms get better and the agreement gets better too. I don't know why DEIM doesn't like the beach. But in any case. Okay, and we also do a little better in the leverage score approximation in this case. Okay, one last example from genetics. Lung cancer patients that the first 2 principal components classify very nicely. Again, Kundu, Nambarajan, and Drenaeus talk about this example. Almost that same plot shows up in their paper. We can look at what leverage scores give us in terms of how well they approximate the matrix, but also how well they classify these 2 patient groups. If we use all the singular vectors, they don't classify so well. They pick out genes in this data set where roughly half and half the patients are sick or well. As the authors of that paper I just mentioned show, if we only take 2 leading singular vectors, though, we classify very nicely. So the genes that get picked out tend to correspond to either sick or well patients, and not a mix of both. DEIM, on the other hand, is more like the leverage scores using all the singular vectors. Okay. We could say a lot more about that. I want to end here before David gets upset. Okay. So, taught you a little bit about the data reduction problem in dynamical systems. Maybe some of you find that interesting because that's, actually a big problem in large-scale scientific computing. Very interesting problem there that maybe data science can shed some light on. Told you about the DEIM selection strategy, how we can do an incremental QR factorization to approximate the SVD, how we construct the CUR factorization, some theory for it that's lacking in some ways because of these exponential growth bounds, but promising in computations. And so I think this isn't a final word on this problem and this technique, but I think it's something certainly worth developing more and learning more about. Thank you very much.